Okay, so we've defined three different quantum states. You can call them vacuum states if you wish, in Schwarzschild spacetime, in the maximum analytic extension of Schwarzschild spacetime. So there's the Bowler state, there's the Unruh state, and there's the Hartle-Hartley state. These ones defined in terms of the in and out modes. So that's the in modes, that's the up modes. These are positive frequency with respect to t, Schwarzschild coordinate time t. This one is defined in terms of, well, this one is defined, you still in, and instead of the little up, we have the capital up and the capital up bar. In some sense, it's thermalizing the upgoing modes. These capital up are really, they include the thermal factor. We'll see this, so we'll see this more explicitly in today. But swapping the up modes, little up modes by the capital up modes is really thermalizing the up modes. It's not thermalizing the in modes. What this really means is you're going to have thermal radiation coming out to sky plus. The capital, the Hartle-Hartley state has that instead of the little in, you have the little in bar and also capital ups. So it has thermalized both the in modes and the up modes. What this will really mean is that there's going to be a thermal bath. You've got thermal radiation, if you wish, coming in because you've thermalized the in modes. You've got thermal radiation coming out because you've thermalized the up modes. The radiation coming in, the flux of radiation coming in cancels out the radiation coming out. So there's no net flux of energy or angular momentum in this case, and it just represents a black hole in thermal equilibrium with its own state. So I'll show this a little bit more explicitly later on. But just to give you an idea, some insight or some heuristics as to how things happen. This effectively thermalizes the up modes. You're going to have thermal radiation coming out, a flux, a net flux of radiation emitted by the black hole. That's Hawking radiation. You have thermalized the in modes. Here you have thermalized both the in modes and the up modes. There's the net flux of radiation coming out, counterbalanced by a net flux of radiation coming in, and so that will give you a thermal bath. So net flux going out to sky plus, and it's at length. So it represents a black hole evaporating by an emission of Hawking radiation at late times on sky plus. This one, it has a bath, a thermal bath. So there's a net flux of thermal radiation going out. In here you've got the thermal bath. In here you've got no radiation to sky plus or coming in, neither going out to sky plus or coming in from sky plus or from sky minus. So I'll show this, I'll give this is just to give you a preview, if you wish, of what we'll see later. Okay, so the properties of the quantum states. So that's really what we'll do today and the last thing of the course. So the properties are really inferred from the renormalized expectation value of the stress energy tensor in a quantum state, what we call the R set. Okay, so remember, in Einstein equations you've got the Einstein tensor, which is classical, some constant, and in here you put in this is what we call the R set, the renormalized expectation value, renormalized because it diverges otherwise in its ultraviolet divergences as x prime goes to x. Renormalized expectation value of the stress energy tensor as an operator, now we've quantized the field, in a certain quantum state psi. Okay. So this is what goes into the semi-classical Einstein equations. The properties of this R set is really what we mean by the properties of the quantum state. Whether there is flux of radiation, whether there's a bath, there's nothing, whatever. Okay. So how do we calculate this? For this, we want to calculate this for these three different quantum states: psi equals Bohr, Unruh, and Hartle-Lagrange. I'll give you a sketch of how to do it. It's very hard to do. But I'll give you a sketch of how to do it and the properties of this. So first of all, you want to calculate. First of all, you want to calculate the unrenormalized one, the non-renormalized one. Then we need to renormalize it. But first of all, we need to know how to calculate this. So the way to calculate this is I gave you an expression for this ages ago. I didn't give you an explicit expression, I gave you roughly what it looks like. So I told you that you had to apply a second order differential operator on a 2-point function. I think I told you this. So I didn't give the form, the explicit form of that differential operator. In 4 dimensions, it's this. For a scalar kit, so this is for 4D. This is for massless, I think it's massless case, massless scalar field. Okay, so the prime here is we're going to apply this operator on a 2-point function. 2-point function because it depends on 2 points in the spacetime, x and x prime. This tells you that this is derivative, covariant derivative with respect to the point x. This is with respect to x, and this is with respect to x prime. Xi is just the coupling constant between the field and the background, and the Ricci scalar. So Xi, I told you ages ago what it was. When we were doing classical field theory, we went through this. So this form, I mean, I'm giving it to you, but we won't actually use it. But just so that you get an idea of what things involve. So this is what we call box or the down version. This thing here is just the Einstein tensor. Yeah.
The 1, 2, the third there, minus 2, yes.
2 Xi. Xi.
No, but the what is the prime? Is the
Oh,
mu?
sorry. Yes.
I suppose the mu.
Yeah. I don't have a prime here.
suppose there is mu because with not we would be together with the first term.
Yeah. Not sure that's the logic. I'm not sure that's the logic. Yeah, so there's no current. There's no current. I mean, it's just the way it is.
The second one to also don't have the prime.
Yeah.
No, I mean the second.
Yeah. No, I know this one doesn't. So.
Otherwise you won't be able to define that box, right? If one is prime.
So, I think this is correct. We're not going to use this anyway. I'm just giving it to you just for you to have an idea. You can find this in many books. So this is Xi, well, G nu Xi R. And all this Xi R, you can just replace by box. Remember that box minus Xi R phi is that's the Klein-Gordon equation. So you can do that if you wish. Now that's applied on a two-point function. That's the Feynman-Green function. I don't know. I can't remember if I talked about this. In a certain quantum state psi. Have I talked about the Feynman-Green function? No. Okay, it's the Feynman-Green function anyway. I'm not going to get into many details. It's a green function because it satisfies the Klein-Gordon equation, and instead of being a homogeneous solution of the Klein-Gordon equation, it satisfies this with a four-dimensional invariant delta Dirac distribution. There might be a minus here, modulo some constant, innocuous constant. So that's what we mean by green function. Okay, it satisfies the green function equation. Now what matters is that the Feynman-Green function is given by this, where t here is just so it can be any time. Okay, you can take it to be Schwarzschild time if you wish. It just, you want to time order the 2 points x and x prime. You know which one is to the future of which one. That's all that matters. And plus, this is G plus. I'll define now what this is. So t just tells you x, sorry, delta t is t minus t point. Is the point x is to the future of the point x prime. Note that I don't mean in the causal future. Okay, they don't have to be causally related. They can be, spaceman or. So if x lies to the future of x prime, you take this guy, and otherwise you just take what we call G minus, which is just the inverse, is G plus x prime x, which is in fact G plus x prime convex conjugate. Or a factor of I multiplying all this. Now, this guy, G plus, this is the Feynman function. This is the expectation value on the state side. So note that I put, every time I put this expectation value and I put a super index for a state, what I mean all the time is expectation value in that state of whatever operator I have in state. So this is, well, phi x prime. Okay. Is this a green function? Is this a green function?
Should be.
Why?
Well, if you take that what's here,
Yeah.
except that we should be three-dimensional green functions.
Why?
Because when you say x here, you say the whole value of x, or just t, r, whatever, or just there's
Yeah, x is space-time point.
Okay, so
X is a point in the manifold. I hope
yes.
this has been clear all the way.
No, it's not that it's sometimes it's just sometimes it isn't. It's sometimes
Yeah,
not.
you're right. Maybe sometime I use this Cartesian coordinate. That could be true.
But
I hope that it's clear from the expressions when it's a Cartesian. It has ever barely been a Cartesian coordinate. It usually it's a space-time point. But I hope it's clear from the expressions when it's a Cartesian coordinate. It's space-time point. What happens if you act with box in this?
It's zero.
It's zero, right? Because this is an element of x, so box will just act on the phi. And box minus xi r is equal to 0 in Schwarzschild anyway. So this is a homogeneous solution of the Klein-Bode equation, both with the operator with respect to x or the operator with respect to x prime. Another question, so why is this a green function, this is not a green function? Well, because you've got thetas here, you've got step functions. You differentiate the thetas and you get deltas. Okay? So that's where the distributional bit is coming in. Is this regular? Does this diverge or is it regular?
This should be regular, because it's two different points.
Right. So in principle, it is regular. You could find for certain quantum state in a certain space-time, you could find some irregularities, but in principle, that's regular. Certainly when the points are close, so that as long as x and x prime are not the same, and in fact when they're not separated by a null geodesic, that's finite. Now, if we take x prime goes to x, that diverges, and we have to renormalize it. So I just wanted to give you this because we're not going to find explicit expression for the standardized tensor because it's a mess, but we will find it for the what is called a weak operator. Weak, not in strong weak, but W-I-C-K. So what that is phi squared. We're going to find the expression for phi squared. So, strategy tensor, you just need to take derivatives of phi squared in some sense. Okay, so we're not going to do it for the derivatives of phi squared, we'll just do it for phi, we'll just look at the explicit expressions for phi squared, not for the derivatives of the phi squared. So if you want to find the R set, you need to take the derivative of phi squared. Now, for phi squared, so this would be the limit as x prime goes to x of phi x prime, but this must be renormalized. Okay, this is not really well defined. So we want to calculate phi squared x prime goes to x of after renormalized. So what we do is we take this guy and then we subtract from this a term which we call phi squared diff for divergence. Okay? You subtract from this a divergence, then you take the limit x prime goes to x. This has been found by Christensen. It is obtained by Christensen 76 with PRD, and I can't remember the page number. He's got two papers, and essentially, well, this is equal to 1 over 8 pi squared sigma x. This is for massless case and conformal coupling and vacuum spacetime. Okay, so massless, we're already doing just massless anyway. I've chosen xi to be equals 1/6, which is the conformal coupling value, and vacuum. All this calculated in a vacuum spacetime. Here the symbol for the vacuum spacetime is a vacuum spacetime like Schwarzschild. Now, sigma, what is sigma? An Irishman, sing. It's called the sigma wall function, in fact. So, sigma is a biscalar. It's a 0-0 tensor, if you wish. It's got no tensorial indices, and it depends on two spacetime points. Okay, so this is called Sing's wall function. Physically, what it is whenever the points x and x prime are sufficiently close, that can be defined properly. Okay, but when they're sufficiently close, there's a unique geodesic joining the two spacetime points. This is valid for any spacetime. You can always, if you take an arbitrary point in a spacetime, you look a sufficiently small neighborhood around that point. In a sufficiently small neighborhood around that point, there's a unique geodesic joining any point in that region to the point x that you've chosen. In fact, the really proper way is that geodesic must remain within that region. So you choose a point x, there's a neighborhood around that point such that x and x prime are connected via a unique geodesic that remains within that region. That region is called the normal neighborhood. And you can always do this. I mean, that is true in flat spacetime. In flat spacetime, you never have multiple geodesics joining two points. In a black hole spacetime, you can have no geodesics. You have geodesics going around the black hole, and so joining two points. Okay, so what this is 1/2. It's 1/2 of the physically, it's 1/2 of the geodesic distance between x and x prime This is when it's only well defined when X prime is sufficiently close to X. Okay. Now, we don't care, this is not well defined for X prime far away from X in most spacetimes. Certainly, certainly in Schwarzschild spacetime, this is not well defined in the sense that it's not unique, because there's not a unique geodesics joining any two spacetime, any 2 points in Schwarzschild spacetime. There isn't a unique geodesic. If it's sufficiently close, that is true for any point in Schwarzschild spacetime or any spacetime. And all we care about is that it's sufficiently close. We're going to take the limit as X prime goes to X. So we don't really care if when X prime is far away from X, there's multiple geodesics and S sigma is not well defined. All we care is what happens. We're going to take the limit, so all we care is what happens near, for X prime near X. Any questions about this? My students know this inside out, at least a bit.
It's a squared, right?
Yes, you're right. 1/2 of the squared of the geodesic distance. Thank you. Now, the defining property or equation is that 2 sigma is sigma alpha, where sigma alpha is the covariant derivative of sigma respect to x alpha. So in order to find sigma, you just solve for this equation. Now, what you do is, all we care about is the small, we're going to take the limit as x prime goes to x, so all we care about is small distances. So you insert sigma so delta x alpha is x alpha prime minus x alpha. It's the coordinates, it's the alpha coordinate of the point x prime minus the alpha coordinate of the point x. So I'll show now this, the leading order is trivial, I'll show it now. And then you can do higher orders, alpha, beta, gamma. You can write it like this, and you can go to higher orders. In fact, we will need a higher order. We'll need, this will be 0, we'll need this one, and the next order. But in order to find sigma for small distances, for x prime sufficiently close to x, what you do is insert this into equation 1, expand it for small delta x, and obtain the value of A. So from this, well, first of all, you need to take the covariant derivative of this. That's rather trivial. And then on higher orders, and it yields that A alpha beta gamma is minus 1 for G alpha beta comma gamma symmetrize. You symmetrize over the three indices. So you can try this as an exercise. the leading order, I'll just check now the leading order, which is trivial. So I've given you the form of the leading order term in it. That's trivial. You've got sigma alpha. So let's just take the leading order. So that G alpha beta.
Mark?
Yeah.
Sorry, maybe a bit lost. How do you get the value A alpha beta gamma?
So all you have to do is just put it in here and expand for the small delta x. And equate the left hand side to the right hand side. And that will give you this value. Okay. So I'm going to show you the leading order. So this is the next to leading order. I'm going to show you the leading order, which is totally trivial. So this is sigma alpha. Sigma alpha down is G alpha whatever gamma delta x gamma. This is sigma alpha up. This has to be equal to 2 sigma. So it has to be equal to G alpha beta. But that is indeed the case because G alpha beta, G alpha gamma is G beta gamma. So this has to be equal to beta gamma delta x beta delta x gamma. Okay, I'm higher order, of course, but this tells you this is a check that the leading order that I gave is correct. And you do the same thing to next to leading order. Now let us look at this in Schwarzschild spacetime and for particular. So by the way, when I write the limit, when I say phi squared renormalized x equals to x of stuff, you can take the limit in whichever way you want. You can follow space-like separation, time-like separation. I'm not sure about null, in fact. You might have to avoid null along a null direction. But otherwise, you can choose whatever you want. So let us consider separation only in time and in Schwarzschild space-time. So delta x alpha is just well, in fact minus. So by the way, I've made in what I'm going to give, I've made a sign mistake somewhere. So if you can find the issue. So I'm not too sure where I've made the sign mistake. I think it has to do with the fact that it's defined delta x alpha prime. That delta x alpha with x alpha prime instead of in this way instead of minus that. In any case, definitely by delta t I definitely mean t minus t prime. And so the point x is t r theta phi, whatever, an arbitrary point in space-time. X prime is t minus delta t r theta phi. Okay? So the same angle, the same radius, all it has, it's separated in time. Okay, so in this case, sigma, well, you go to your expression here. So now delta x alpha and delta x beta, the only components, the only non-zero components are the t components. So this is 1/2 of gtt times delta t squared. What about a? What is a equal to?
looks like the affine connection. This is the derivative?
This is the partial derivative.
Yes.
Time derivative of GTT times minus 1/4.
So Schwarzschild space-time is static.
It's all 0.
So any time derivative of any component of Schwarzschild is going to be 0. So it's 0. So you only have ATTT because the only non-zero component of delta x alpha is the t component, but this is 0 because static. Note that it's symmetrized, okay, so you're not, the fact that alpha, beta, and gamma are all t, it means that you always have a derivative in time. And then higher order terms, a delta t4 term, which in fact we need. So GTT is this minus 1/2, 1 minus 2m over r order delta t to the 4. Now, we need the delta t to the 4, so you can do it. You can do it for this particular case in Schwarzschild space-time and this particular separation. Things get, like you can see, a lot easier if you choose this separation. So you can do it for this specific, this was for general separation. You can do it specifically for this separation, and you get the 1 over sigma is this. Now, and so this is the order 1 over separation squared, 1 over the separation not squared is just 0. This is an order. This is an order. This is a regular term. And then you've got higher order terms, but these guys will go to 0 as you take the limit x prime goes to x. Okay, so remember, phi squared is 1 over 8 pi squared sigma. And you choose your separation in any way you want. We choose it like this, and you find this. Okay? So this shows explicit. Oh, so two things about this. First of all, I've got the sign wrong here. So I think this comes from the fact that I've chosen delta x like this instead of the inverse. But I'm not sure because this is delta t squared, so I'm not too sure about that's the reason. But in any case, I've made a sign mistake somewhere. And also I haven't proven this, but you can, if you take this particular separation, explicitly already from the start, this particular separation, expand this equation with that particular separation, you can get that. So this shows explicitly, rather explicitly in Schwarzschild space-time, how the divergence comes in whenever the 2 points, one point goes towards the other point. If you take x prime goes to x, or delta t goes to 0, this diverges quadratically. It also shows another interesting thing. You can't just throw away divergences willy-nilly. Like you can just say something that, so remember, we are renormalizing, so we are phi squared renormalized in some quantum state is the limit as x prime goes to x of phi squared not renormalized and, well, phi regularized minus the divergence. Okay? You don't just subtract infinities willy-nilly. You have to do it, you have to find this in a covariant way. Okay? This Christensen found this, and this comes from prescription that I gave the axioms, Wall's axioms. So that's what will obey Wall's physical axioms. So as I say, you don't just subtract, this is a divergence as x prime goes to x, but you also need, this is a finite term that you need to include whenever you renormalize it. Renormalize it, not just purely throwing away divergences willy-nilly. You need to do it properly, covariantly, and following Wall's axioms if you believe in them. And that includes, in particular, a finite term. Any questions? Okay. So, let us find, so we found this, now let us find this other guy. We've got three vacuum states. I'm going to do it explicitly for the Unruh vacuum state, which is the one that contains a mix. So find phi x prime in the Unruh vacuum state, unrenormalized. Okay, so for Unruh, we expanded the field in terms of the little inmodes. The left and the right ones, the capital up modes and the capital up bar modes. And you need to include the Hermitian conjugate of all this. Now, we're only going to do it outside the black hole. This is region 1. This is region 1 of the space-time. Okay, so we're going to calculate your set outside the black hole. So this is, the left guy is just 0 for x in region 1. Okay, this, the fine left only have support in the left region, region 3. The capital up modes, we saw that they're equal to this. You can rewrite this, and then the up, this is little up. And these are left, the left and the right ones. Now again, this is the left is equal to 0 when you're in the right. You can rewrite this. Let's call alpha pi Aula kappa. So you can rewrite this as exponential of alpha over 2 chain of alpha squared. The capital up bar modes, that's the same coefficient in front, and now you've got, this is exponential minus alpha, phi lambda up r star. Now again, this is 0 for x in region 1. Okay, so let's, so phi for x in region 1 is just equal to this. it's equal to this. Now let's apply this onto the Umbro state. So phi applied onto the Umbro. Well, so all these guys, these annihilation operators annihilate the Umbro state. Okay, so that will give you 0 whenever this is applied into A lambda in R onto the Umbro state is 0. That's the definition of the Umbro state. Same thing for the capital bar and same thing for the capital O. Okay? So all that will survive is the Hermitian conjugate. The Hermitian conjugates don't annihilate the Umbro state, they create particles when the field is in the Umbro state. So, as I say, what will survive is the Hermitian conjugate of this, and the corresponding coefficient has to be complex conjugated. So that's that. And now we need to take the adjoint of that and sandwich it with this. Okay, so we have phi x and phi x prime. So the indices corresponding to the x prime, to the first one, I'm going to call them primes. Okay, so this sum over L primed, M primed, omega primed. The integral over omega is always between 0 and infinity. Okay? So I'm not even writing that out anymore. And then the same thing again, instead of primes, unprimed indices, and the Hermitian conjugate of this. So sum over Lm omega A lambda in R, Hermitian conjugate, phi lambda in R at x primed, complex conjugate. Alpha, when I write alpha primed, by alpha primed obviously I mean on pi omega bar kappa, okay? The prime denotes primed index. So here it's primed, in the first expression it's all, first factor it's all primed. Here, again, you take the Hermitian conjugate of this. Okay. Okay, so now what you want to do is you apply the commutation relations between A and A dagger. Because now we want to, this does not annihilate this, the same way that the A dagger does not annihilate U, but you want to swap the order of the A's and the A daggers so that you get A's on the right hand side acting on U, and that will give you 0. Okay, so you do that. So now, as I say, commutation relations between all of them, all these operators. Obviously, the ins and the ops commute, the ops and the op bars commute, regardless of whether they are daggers or non-daggers. Between the ins and the in daggers, the commuting in the commutator is equal to 0. So this is also true for capital op, and it is also true for capital op R. Replace in by capital op. Or capital op bar. So now you do that, and all you get is a delta that will allow you to go through one of the sums and integrals. So now the primes, all the lambda primes are just lambdas. Because of this, you've killed one sum and one integral. And you only get, because the ins commute with the ops, you only get this guy times this guy. You get this guy times this guy. And this guy times this guy. That's what this is. Okay, so now we've got exponentials. Exponential alpha, 2 shine alpha term. This is just 1 over 1 minus e to 12 and exponential of minus alpha. Is equal to this. Okay, and now you put in the explicit expressions for phi in or up to the right. This is just the n in or up times r in or up times y times exponential of minus I omega. And this guy, this was 1 over square root of 4 pi omega. You use this And we also, Schwarzschild space-time is spherically symmetric. A consequence of that is that the radial functions do not depend on m. Okay? All the n dependence goes into the y's. So you can really take the sum over m, which is from minus L to L, you can take it in, all you have is y's times, I'm missing complex conjugate here, right? Yeah, it's complex conjugate. So all you have is y's times y complex conjugates. Y times y's complex conjugate of y. Y times complex conjugate of y. And you can do the sum over m for that. So the sum over m between minus L and L of y ln omega, y l m omega prime. That's just 2l plus 1. 2l plus 1 over 4 pi l cos gamma. pl cos gamma. So as I say, you can just take the sum over m inside here. The only n dependence is in the y's. So you can just do that sum. And this is, obviously it should be like this. Gamma is the angular separation between x and x prime. Okay? Obviously it shouldn't depend on theta and phi. It's spherically symmetric. You can always rotate the sphere in a way that the angle of separation is along either just theta or either just gamma or either just phi. All that matters is the angular separation. It doesn't matter if it's in the theta direction or the phi direction. Okay, so you put all this and you get 4 pi squared coming from a 4 pi from here and a 4 pi from the angular part, r squared, because I missed, so I'm here missing a 1 over r. So r squared from this, and then the sum from 0 to infinity of 2l plus 1 exponential high omega delta t, or in l omega r. That's a very important expression. So remember before that I was saying for the onward state we've terminalized the up modes, we haven't terminalized the in modes. I gave you a preview of this. You can see how the terminal factor is only in the up modes. There is no terminalization of the brackets because the exponential is multiplying both terms. Okay, so this is what gives you Hawking radiation coming out to scribe plus. You've got a terminal factor in the up modes. You can do the same thing for the Hartle-Hawking state. In the Hartle-Hawking state, you've terminalized both the in modes and the up modes because we use the capital in as well as the capital up. So you do the same for the Hartle-Hawking state similarly. So you can do this as an exercise. You do this for the Hartle-Hawking state. So the up mode part is just the same. This is true obviously only for x and x kind in region 1. The up modes is just the same as for the Umbro state because it uses Hartle-Hawking state uses capital up and capital up bar just like the Umbro state. So this gives you the up part is just the same. What's happening? I'm missing a term here. Okay, so yeah, so there was curly bracket and I'm missing a term. Right. Exponential of I omega delta t. So this is the sign of delta t has changed now because the complex conjugate one is x, not x primed. So this term here comes from this guy here. You can see the 1 minus 1 over 1 minus 2 alpha. And now this term here Okay, so now going back to where I was, there's this total symmetry now between the in modes and the up modes. So wherever you have, you know, the Hartle-Hawking state thermalizes equally in and up modes. So there's a total symmetry. This is just, as I say, this is just, so from here you can infer the expressions in the Bowler state and the Hartle-Hawking state. Why? Because, as I said, the up part has to be just the same. So the up part, this term is just this term here. And the in modes, there's this total symmetry between the in modes and the up modes. So in the up now, you just have the same thing for the as for the in. Now you have to do it explicitly, but that's what you find. And you can, heuristically, you can see why that's the case. So that's the first term. And then the second term, as I say, is just the same. It has to be the same as for the Umbro state.
Mark, isn't there an omega in the denominator from the normalization? Or omega is
Yeah, there should be. There should be. Yes, you're right, yeah. Thank you. Okay. So yeah, so the other term is just like, well, for the up part, it's just like in the owner state. as I say, there's a symmetry between the in modes and the up modes, so you just add now the same thing for the in modes. Okay, so that's another important expression. As I said, from this expression you can already infer the expressions for the Hartle, Hawking and Bowler states. What does, now we need it for the Bowler state. What is Bowler? Well, Bowler is defined in terms of little in modes, treated in the same way as the Umbro state does. It does not terminalize them. Okay, so the in part, in the in modes part of the Bowler, in the Bowler state will be just the same as in the Umbro state. Also, it treats the up modes on the same footing as the in modes. So the up mode part will just be just like the in modes, just with superindex up instead of in. So you can readily infer, but you should do it as an exercise, you can already infer the value in the Bowler state. So 4 pi squared or squared sum over L. As I say, the in modes are just the same as for the Umbro state, and the up modes are just totally symmetric between in and up. So you just replace in by up in here. And that's it.
And the explanation. Indeed.
And the explanation. Thank you.
The term of the polynomial, the Legendre polynomial.
Ah, shite! You're right. You're right. So I'm missing the Legendre polynomial everywhere. So PL cos gamma. PL cos gamma. PL cos gamma. Thank you. In practice, because we're just separating the times, we're just taking a time separation, then the gamma won't matter. PL cos gamma for gamma equals 0 just equal to 1.
Oh yeah, that's for time separate only, right?
Well, so this is set general.
But okay, if we had taken any separation, we would get it.
Yes, this is, we have taken the general. The only place where we used time separation was here. This is for time separation only. For the phi div, phi square div. The explicit expression we found for phi square div was only for time separation only along time, the time component. This is totally general, except obviously x for x and an x prime in region 1. Okay, but any arbitrary point in region 1. So, well, we already have all the expressions, and all you have to do is put them together. The unrenormalized part and the divergent part. So define mu psi in the following way. Okay. All I mean is mu is just the integrand, the omega integrand. Okay. This is gamma. And then the renormalized weak operator in the psi, whatever, psi can be Bohr, Unruh, or Hartle-Hugging state. This is just x equals to x of, phi x point unrenormalized. So now you can take, after you subtract the divergent terms, now you can take the limit, x prime goes to x. So I'm taking r prime to be equal to r. Certainly gamma equals 0. And I think we can take already delta t equals 0. So I think we can already take delta t equals 0. So this term here. Well, okay, I haven't done this, but you can rewrite this divergent term in this way.
Omega.
Yes. So let me see. So in here I'm using. So this shows rather explicitly how the coincidence limit divergence, it really is an ultraviolet divergence. It's a large frequency divergence. This guy, which diverges as delta t goes to 0, is coming in from the fact that the integral of omega as between 0 and infinity, it diverges. And it gives you, so if you put in an exponential of minus I omega delta t, let me give you the expression. So this uses, in here I'm using the fact that I'm using this. So, as I say, this shows that the coincidence limit divergence of 1 over sigma, or phi squared, is coming from, it's an ultraviolet divergence. That this integral diverges for large omega whenever delta t is non-zero. Whenever delta t is 0, what happens is you've got oscillations with infinite frequency that kill off the omega term, if you wish, so that the integrand converges for delta t non-zero.
Yeah.
For delta t 0, obviously, this divergence and the right-hand side divergence.
And the finite part.
Yes, and the finite term you have to include as well. So this is minus m squared 48 pi squared r to the 4 1 minus 24. Okay, so yeah.
Look at the expressions of the expected value